Okay. Good afternoon, everyone. Um, so, without wasting time, we'll be looking at how to do some check over a product of multilinear polys, right? So, first of all, like, why is it even necessary? Like, why is it necessary that we're even talking about like doing some check over a product of multilinear polys? Does anybody have any idea? Like, why are we doing some check over a product of multilinear polys? Okay, so f of a, b, c, right, was equal to addi a, b, c times is it addi plus 1, right? wi b plus wi of c, right, plus more y plus 1 a, b, c wi of b times wi of c. Does this look strange? Does it look strange to anybody? No. Okay. So based on this, we can see that here we're performing a product of multilinear polys, right? Also here we're performing a product of multilinear polys. When we multiply two multilinear polys, what do we get? A multivariate. Do we agree? Do we agree? So if we have like 2ab times 3ab, what are we going to get? 6a squared b squared, right? So this is no more in the multilinear domain, right? It's now a multivariate. Sorry, multilinear is still multivariate, right? But we get the idea, right? Yeah, okay, thank you. So we get a non-multilinear polynomial. When we multiply two multilinear polynomials, we get a non-multilinear polynomial. Okay, so but we still need to perform some check over this guy, and that's what we're going to be looking at, right? If we decided to, we're basically working in evaluation form, right? And if we have two polynomials in evaluation form, how do we add them? Just a random question. According to their indexes, right? So you have two polynomials in evaluation form. Let's say still this 2ab plus 3ab. over 0, 0, 0, 1, 1, 0, 1, 1. This will give us, what will 2ab give us? 0, 0, 0, 2, right? And this guy will give us, so if we add them element twice, we are going to get 0, 0, 5, right? Adding these two polynomials, what do we get? Like in the coefficient form, we get 5ab. Is this 5ab over the evaluation form, right? It is. Okay, good. So now, how about multiplication? If we want to multiply two polynomials in evaluation form, how are we going to do it? Huh? No, I'm talking of like evaluation form.
Yeah, you multiply like each.
Okay, so wait. So we say 2ab times 3ab, right? What should be the answer in the coefficient? 6a squared b squared, right? Okay. So this is 2ab, right? 0, 0, 0, 2. And we are saying we should multiply it by what? 0, 0, 0, 3. And what do we say our answer will be? Yeah, how did we say we are going to do it first?
Multiply 1 by the 4.
No, I think if we should know the answer we're expecting first before we can.
No, let's. You want to reverse engineer?
And yeah, if we know the answer we're expecting, we wait like.
Okay, well, like, does anybody have any?
Just like 0.
Okay.
Times every element. Add the answer together.
Honestly, it could still give us 0, 0, 0, 6.
Exactly.
Yeah.
Yeah.
Okay, 0, 0, 0, 6.
Yes.
But you are saying something.
Like each element in the left guy multiply every
Like
element in the right guy.
this one,
Yes.
we multiply by
Every
everything.
element.
It
And
will
whatever
give
you are
you
getting, you're going to add it together.
Okay. So that will be like 0 times 0,
Yeah.
0 plus 0 plus 0 plus 0, right?
Yes.
So this one will be 0 plus 0 plus 0 plus 0, 0 plus 0 plus 0 plus 0. And this last one will be 2 times 0, right? 0 plus 0 plus 0 plus what? 6. Sorry? Go over it. Okay. So he's saying we take this guy, right? This guy. I will use him to multiply all the elements in this one. Right? And we sum it together, which is this line. Then for this second guy, we use him to multiply all the elements here to get this guy. Does it make sense? Okay. So basically the same thing. So we get to 2, right? So if we add all of them together, what are we going to get? 0, 0, 0, 6. Okay. So the question now is, are these two things the same?
You don't know, that's very fine.
Let's verify. Okay. So we have 6a squared b squared, right? And what are we going to evaluate it over? The Boolean hypercube.
Yeah, they are the same.
Huh?
They are the same.
The both of them are the same.
Yes.
Interesting.
0 square is 0.
Okay, but like, what are we evaluating it over first? The Boolean hypercube.
Yes.
Do we all agree?
Yes.
We all agree.
If
We're evaluating it.
Francis, if
Yes.
6a square will give this, that means 6ab will also give this.
Okay.
Exactly.
But are they the
6ab
same
also have
polynomials?
They are different.
It's supposed to be like much more longer.
Hmm.
Yes. Because now
Okay.
you have 4 variables, they're supposed to have like 16.
Interesting. Well, let's see.
There's 2a squares.
Let's see, right?
A square, b square.
So this should be 0, right?
Yeah.
0, 0, 6.
Yeah.
Are they not the same?
Yeah, they should be.
But if we
They are the same, right?
Yeah.
Over the Boolean hypercube, they are the same. But if you take other values outside the Boolean hypercube,
They'll be different.
And if you compare this with 6ab, there's no difference evaluating this over the hypercube. And then evaluating 6ab, you still get the same. So we cannot say,
So
if
six-
we are giving this evaluation form, we cannot tell if it is 6ab or 6a square b square.
Exactly. Right? Because two of them pass through this same point, right? So what was the thing we said about two polynomials um, of a different degree, right? Or can we remember the Strasbourg lemma? We can remember the Strasbourg lemma. So what does the Strasbourg lemma say?
If two polynomials are equal, they equal at all the points.
Okay. Well, here we can see that over the Boolean hypercube they are the same, right? But this polynomial has a higher degree, right? So the both of them pass through the same point over the Boolean hypercube, right? But that does not necessarily mean they are the same because they are of different degrees, right? So in order for us to get the correct evaluation representation of this guy, over the Boolean hypercube is sufficient to get the correct evaluation of this guy, right?
Yeah.
Do we agree? Like evaluating this guy over the Boolean hypercube is sufficient
Yeah.
to get his evaluation form representation. We agree.
Yeah.
But is it sufficient for this guy?
No.
no.
It's not, right? Why?
Please remember.
No, not about remainder. I thought to hear something about degree.
You need a D plus 1 to the degree is 4. It's supposed to have like elements of like the array here, but it's supposed to be about 16.
About 16.
16 elements of
16. 16 is what? 2 to the
power of
2 to the 4. Okay, let's see. So, but because this guy is a polynomial of a higher degree, we can't fully represent him by the evaluation over the Boolean hypercube, right? So we now need to go a step further. We need to go out of the hypercube. We're not going out of the hypercube per se, but we are adding more fidelity to this representation. I'm saying fidelity now, you may not understand, but when it eventually starts making sense graphically, then like you'll be able to understand what I'm saying. But then let's see, still 6ab a square b square, right? Let's represent him over the interpolating setting 0, 1, 2, not 0, 1 again, right? So we're using 0, 1, 2. So we have still two variables, right? 0, 0, 0, 1, 0, 2, right? 1, 0, 1, 1, 1, 2, right? 2, 0, 2 1 2 2. Is this enough?
As in base 3.
Eh?
As in base 3.
Yeah, base 3. So evaluating over this guy will be 0, right? Do we agree? Okay. So how about 0 1? 0 0 2 1 0 1 1 1 2 1 2 is what? 24 2 0 2 1 24 96. So this is the representation of this guy in evaluation form, right? If we check over the Boolean hypercube, both of them agree, right? That's 0 0 0 1 1 0 and 1 1. But then because of this extra information that we added, we can see that they are not the same polynomial, right? So if we should evaluate this guy over like using the base 3, we are going to see that the answer we are going to get at this other point will be different. Do we agree? Do we agree? Like if we evaluate this 6AB at still over this Boolean hypercube with an interpolating set of 0 to 2, we are going to get different values at this point, right? Do we agree? Any need to do it? We have a lot to do, so let's just, but we agree. Are we sure? Are we sure we agree? Okay, let's quickly verify. So that's 0 0 0 1 0 2, right? 1 0 1 1 1 2 2 0 2 1 2 2. So 0 0 0 1 0 2 1 0 1 1 1 2 12, right? 2 0 2 1 2 2 24. So we can see like at 2 2 here is 96, here is 24. At 2 1 this is 24, this is 12. Yeah, at 1 2 this is 24, this is 12. So basically, like, this is enough information for us to know that they are not the same polynomials, right? But the thing now is that when we
So this is the trilinear hypercube. What do you call it?
usually call it 3HC.
Okay, 3HC.
Yes, that's what we usually call it. I don't know if there is a no, it's hypercube. 3 hypercube. Not Boolean again, it's not 2. You get. Yeah, you can call it exactly. So I don't know, there should be a name for it, but I don't know what the name is. So do we understand up to this part?
Yeah.
We all agree.
And
We are-
if you look at the both self, it's basically okay, it's not
Yeah. So like depending on the values and like the degree of each of the this A is square here and B is square. So that's kind of like the you can basically use it to get the difference, right? But that's another talk for another day. So So we can see that in order to do this multiplication, right, if we wanted to do it in evaluation form, we had to blow up the interpolating set, right? So that will mean more space requirements, right? But then we'll be 100% sure that this polynomial in evaluation form we'll be 100% sure that this polynomial in the evaluation form is what we expect. But we want to still be able to do, like, our goal basically is to do some check over a product of multilinear polynomials, right? And we know that if we do that outright multiplication, then the Boolean hypercube is not sufficient to represent the information. Do we agree? If we do this outright multiplication, then the Boolean hypercube is not sufficient to represent this polynomial.
Yes.
So we still want to, like, we're basically looking for a way to enable us perform the Sumcheck protocol, right? But not necessarily blow the size of the array up.
Okay. You are still limiting it to this, the Boolean hypercube.
Yeah, we're still limiting it to the Boolean hypercube. But then the polynomial that we are expected to get, right, which is this polynomial, we want to be able to, like, perform some check on it. Do you get?
Yeah. Isn't it possible for us to plus one two since I was next to I was on the results and then
It's like, you know, okay, how does the Sumcheck protocol work? You have a polynomial. Let's say you have a polynomial 2ab, right? You skip a and sum b over the Boolean hypercube, right? It's a summation. And then after the interaction, we do the oracle check. These are just two variables. So I get what you're trying to say, but it will not work. Yes, it will not work. There are some complications to go in that route. Okay, so let's perform the Sumcheck protocol over this guy, right? And then we're also going to perform, it's two variables, okay. And then we're also going to perform the Sumcheck protocol over this guy to see what the Sumcheck protocol will look like in the two cases. Is that okay with us? Sure?
No,
Yeah?
I've not forgotten the representation.
For which one?
This 6a square b square, because you said I want to be able to represent 6a square b square without expanding, and which is what we did with this 3h. So then how are we going to represent this in this form in such a way that it still captures it? I've not been able to answer that question.
Like, to represent it in this form
Yes.
without such that it still captures
Yeah, it still captures
6a a square b square.
Yeah.
The way to do it is by representing it in this form and performing some check over these two guys. So we'll be performing some check over 2ab times 3ab.
Okay, which is now the product of two multilinear.
Yes, which is the product of two multilinear.
Okay, you perform the sum check individually.
Is not exactly individually. You get? So we are performing sum check over two multilinear polynomials. The product, we are performing sum check over the product of two multilinear polynomials. Right? It should have been one way to go about it is to do the outright multiplication, right? Then you perform sum check over this guy, right? But that will incur like space costs, right? Do we agree?
Yeah.
So now instead of doing it outrightly, like doing the multiplication outrightly and then blowing it up to perform sum check, we want to perform sum check on a product of two multilinear polynomials. Is it making sense?
Product of two multilinear polynomials.
Yes.
I'm thinking of how the sum check is going to. Is it like in every iteration of your sum check, at the end you multiply the both of them or something like?
Actually, it's not. If you want to go that route,
Yes.
you will. If you want to go that route, it will be problematic because, like, if you think of like, because of associativity, it won't be correct. Don't worry, we are going to do an example. Well, yeah, so we are going to do an example. So, how are we going to do this now? I think first we should start with performing sum check over this guy, right? So that we will have like something to work with. When we're performing sum check over this guy, we have like something to look up against, right? So let's perform sum check over 6a squared b squared. Should we?
Yes.
Shall we? So that's 0, 0, right? Or should we? Okay, let's do it in coefficient form first. Right. So we have our polynomial 6a squared b squared. I will want to perform sum check over this polynomial. And what is it going to look like? Okay, so I want to perform sum check. We are performing sum check over the Boolean hypercube, right? So let's represent this polynomial over the Boolean hypercube. That's 0, 0, 0, 1, 1, 0, 1, 1. So that's 0, 0, 0, 6. Right? Okay. Right. Okay, so if we sum this guy over the Boolean hypercube, that's 6. Well, in each round of the Sumcheck protocol, the prover is expected to send a univariate polynomial, right? And that univariate polynomial, we can use 2 points to represent it, right? But since 6a squared b squared is, or since the variable a is not a degree 1 variable, it's a degree 2 variable, right? So 2 points will not be sufficient to represent it. Like that univariate polynomial now is going to be made up of 3 points. I don't know if we understand. Okay. So we have we want to generate a univariate polynomial for 6a squared b squared, right? That means we are going to evaluate 6a squared because we are leaving a squared, right? And then we are evaluating b squared over the Boolean hypercube. So at 0, at b equal to 0, right? That's why b is equal to 0, right? And this where b is equal to 1, right? Huh? Where b is equal to 2. Yeah. Okay, no.
We have not gotten to that place now.
Yeah, we've not got to it though. So we remember that what the verifier is going to do is that the verifier is going to evaluate the univariate polynomial at 0 and 1,
Yeah.
right? And for the verifier to evaluate the univariate polynomial at 0 and 1, then the prover basically needs to do that, so which is just this, the sum over the Boolean hypercube, which is this, right? So what are we? Yeah, we're still using the Boolean hypercube. No. We're not using base 3. So that is what I'm. But we are going to use base 3 when we are sending the univariate polynomial. But for now, we are just going to evaluate the polynomial over 0 and 1.
We'll get 6 this way.
So this will be 0, right?
Yeah.
And this will be
6 this way.
6a squared. So this is the univariate polynomial.
Yeah.
Right?
Yeah.
And the prover is meant to send this univariate polynomial to the verifier. Okay. Sorry, we've not gotten the claimed sum. Yeah. The claimed sum is 6.
Yeah.
Yeah. Which is the evaluation at 0 and yeah, like over the Boolean hypercube in 2 variables. This basically. Right?
Yeah.
Okay. So
The verifier will evaluate at 0 and 1.
yeah, and sum it up. So the verifier evaluates this at 6.
You get 6.
Yeah, to get 6. Okay. Then the verifier samples a random challenge, right?
Yeah.
So what should we say the random challenge is?
3.
3. And the prover evaluates 6a squared b squared at a equal to 3. That's 6 times 9, 54, right? 54 b squared. Okay. So this is a univariate polynomial,
Yeah.
but but the prover is going to send the sum of this polynomial over the Boolean hypercube, which is going to be plus 54 1 square. This guy goes, we have 54, which is the new claimed right.
But you can get a new claim sum from the previous univariate, right?
Yeah, the verifier is going to so the verifier is going to evaluate 6a square at r equal to 3 to get the new claim sum that he will use for verification.
Yeah.
So that's 6a square which is 54, right? 6 times 9.
I think, can you separate it? The one the prover is doing and the one because it's kind of like
Okay, mixing up, right?
Yes.
Okay, maybe let me draw a line. We're starting with the polynomial 6a square b square, right? And the prover says the claimed sum is 6, right? So he sends the claimed sum to the verifier and also sends the univariate polynomial, which is 6a square,
Yeah.
right? Right? So it sends 6a square and 6 to the verifier. Are we together?
Yeah.
Okay. So the verifier evaluates 6a square at 0 and 1. This zeroes out, right?
Yeah.
And he gets 6, right?
Yeah.
6 is equal to the claim sum the prover said. So the verifier samples a random challenge r equal to 3. Please, if you have any,
What happened to the B square?
huh?
What happened to the B square?
2.
The B square on the previous side.
No, this is the univariate polynomial that the b square is like this, the initial polynomial. So you're going to evaluate 6 a square b square. You're going to sum it. You're going to skip one variable, which is a, right, and sum it over the Boolean hypercube. That's 6 a square. We're skipping it, and we're evaluating our b over the Boolean hypercube. 0 plus right. This guy goes out. So we're left with 6a square. So which is this 6a square he sends to the verifier. Does it make sense now? So then the verifier, he sends the univariate polynomial and the claimed sum to the verifier, right? The verifier evaluates it at 0 and 1, right? And gets 6. 6 is equal to the claimed sum, so the verifier accepts, right? And then samples a random challenge. So the verifier now needs to get the claimed sum for the next round by evaluating 6a squared at a equal to 3. This is 54, right? So the verifier sends this random challenge back to the prover. Are we following?
Yeah.
Sure. And when the verifier sends the random challenge to the prover, what does the prover do? The prover evaluates the initial polynomial at the random challenge, right? So that is 6a squared b squared which is 54 b squared, right? The prover still sums this guy over the Boolean hypercube, right? Summing it over the Boolean hypercube, we are going to get 54 right? This guy goes to 0 and this guy is just 54. Why is the prover summing over the Boolean hypercube and not?
Why does the prover want to?
Okay. So the prover wants to verify. Wait. I don't know if I got your question right now.
Now, what I'm saying that it's not just to verify that this is new claims.
Yeah.
The prover itself doesn't technically.
Yeah, actually, there's no need for the prover to send this, right? But normally, like, let's just do that because the verifier already has this 54.
What is the kind is that 4 square?
Yeah, the 54 b squared. Okay. So the prover sends 54 b squared, right? And 54, not necessarily because the verifier can calculate this already, right? It sends it over to the verifier. So what does the verifier now do? The verifier evaluates it as 0 and 1. He gets 54,
Yeah.
which is equal to this guy,
Yeah.
right? So he accepts and then samples a random challenge.
Well, when is something random challenge? You're not supposed to
The random
end. You're not supposed to
check.
do your project.
Yeah, that's what. So since it's equal, the verifier samples a random challenge. What should we use as a random challenge? Let's use 2. So the verifier evaluates 54 b squared at 2. So what is this going to give us? 216. Right? And then the verifier also evaluates the original polynomial, which is 6a squared b squared at 3 and 2, right? And what does it give us? Still 216, right? So which is basically the oracle check. And since the both of them are equal, the verifier accepts. Right?
Yeah.
So this is the Sumcheck protocol over like a multivariate polynomial. It looks easy, right? Because we're working in the coefficient form, right? So let's look at it in the evaluation form. So look at it in the evaluation form first before that's going to be long. Okay, so this is Sumcheck. This is Sumcheck protocol in the coefficient form.
Are you sure? You want to do the still creation form or the product?
But the products first, right? Before we enter evaluation form. Okay. I was thinking of the right order, so the coefficient. So you wanted to ask a question. We technically used it.
How?
It's because we are working in coefficient form. That is why, like, you didn't notice. But we used it.
Right?
Yeah.
You sent 6a squared
Yeah.
and you sent 54b squared.
A square,
That's the degree 2 polynomial.
which will be represented with 3 points.
You get like normally there's only one polynomial, which is 2 points. Like you need d plus 1 point to represent the degree d polynomial. So that's why your round poly has always been 2. 0 and 1. But now your
Yeah.
round poly is going to have 3 points. But it's not a quadratic round poly.
So we technically used base 3 as the interpolating set, but why we didn't notice it was because we're working in the coefficient form. I don't know if what.
I didn't get the question.
Okay, so he was asking, like when we were showing this, doing this example, we said that using the Boolean hypercube is not sufficient to represent this polynomial, right? So we need to work over like the interpolating set of base 3, like 0 to 2, which is this point here. Right? In order to represent this polynomial accurately. In order to represent it accurately. So he's asking, like, why didn't we evaluate, like maybe why wasn't the verifier evaluating at 0, 1, and 2? You get? Well, the answer is basically when the prover sent this polynomial 6a squared. 6a squared is a degree 2 polynomial, right? And a degree 2 polynomial, if you want to represent it in evaluation form, is 3 points, which is basically the evaluation at, like if you want to send the evaluation representation, it's going to be the evaluation at 0, evaluation at 1, and the evaluation at 2. Does that make sense? So we technically sent 3 points to the verifier instead of the normal 2 we would have sent. But why we didn't see those 3 points is basically because we are working in the coefficient form. I don't know if it makes sense. It makes sense, right? Does anybody have any question?
I think it will be clearer when we same thing in the evaluation.
in the evaluation form, right? Like it's very easy for somebody to get lost. You're already lost. Okay. Because there are a lot of ways to go about it, and it's good to understand them so that when we are designing our protocol, we are not going to design an insecure protocol, right? Because if the prover, like in the evaluation form, if the prover sends 6a instead of 6a squared,
Yeah.
that's a problem, right? So why we are going to go through all these methods is just to help us to see where potential bugs can come in when we are implementing, right? So you said, so which should I go over?
Yeah. The part where I feel like the linear to verify have to evaluate.
Okay. So like let me just run through it again. So we have a polynomial 6a squared b squared that the prover wants to prove, right? And he sums it over the Boolean hypercube, the 0 and 1 Boolean hypercube. And he got 6. Right? So he wants to prove that the sum of this polynomial over the Boolean hypercube is 6. Which it actually is, right? Do we agree? Okay. So he sums it and he also generates a univariate polynomial in B. He skips A and evaluates B over the Boolean hypercube, which is basically this, right? Like he skips A and evaluates B over the Boolean hypercube, sums it and sends it to the verifier. Together with, he sends it to the verifier, which is this 54b squared, together with the claimed sum, right? So after, sorry. So, first of all, the prover sends the sum over the Boolean hypercube to the verifier, right? And the verifier, he also sends the univariate polynomial, 6a, to the verifier. Yeah. So the verifier evaluates 6a at 0 and 1, right? Sums it and gets 6, and accepts, right? Because this 6 is equal to the claimed sum. Right. The verifier then samples a random challenge, r equal to 3, and evaluates 6a squared at r equal to 3 in order to get the claimed sum for the next round. The verifier then sends r to the prover, right? And the prover evaluates the original polynomial at r to get 54b squared. Yeah, the verifier evaluates at r equal to 3, like this univariate polynomial, in order to get the claimed sum of the next round.
Yes, now we did it in the previous subject. Now when we use that interpolation, linear interpolation.
Yeah.
But since this one is,
Well,
that one cannot work on this.
which one?
That linear interpolation, will it work on this?
Okay, no, it won't, right? Because we are not dealing with
Linear.
linear polynomials again.
Wait, were we always doing this in normal
Yeah, in normal sum check, correct.
Yeah?
Unless you were sending the claimed sum to
Yes.
the verifier. You were sending the claimed sum to the verifier.
Yeah. Referral was also very
But we basically like also talked about it, like that the verifier can actually know.
The last.
Huh?
The oracle.
No, not the oracle, right? Like immediately the verifier samples the random challenge,
Yeah.
the verifier knows the claimed sum of the next round.
I think like it's because we're not sending all the sums. We're just sending one claim sum which the prover is sending. So the verifier is the one that will calculate the successive claim sum so that the prover doesn't have to like compile all the sums.
All the sums.
Sorry, I have a question. If our polynomial is successful with system, we're also going to evaluate at 0 and 1
If
using this question from
yeah,
at 0 and 1
is it the verifier?
to the prover.
The prover. Yeah, the prover is going to is generating a univariate polynomial, right? Is it this part you're talking about?
Yes.
Yes. It's 0 and 1. Right. It's summing it over the Boolean hypercube. So it skips A and sums B over the Boolean hypercube. When we get to the evaluation form, I think like it will make more sense. Like when we do an example with the evaluation form.
The
It's a
difference between this one now and the other one is that in the previous one, all the univariate polynomials that the prover sends to the verifier, they have one
Degree 1.
degree.
Yes.
But currently sending the univariate polynomial with
Degree 2.
that's where the
Yes.
difference is in the coefficient form.
Exactly.
So in the evaluation form, we are going to represent this degree 2 in the coefficient form, which will give us like
In evaluation form,
evaluation form, which will give us like 3
evaluation
three
points.
points.
Like basically like that's just the summary, right? So still the same protocol, but the univariate polynomial in each round will be 3 evaluation points, no more 2. So since it will be 3 evaluation points, we cannot use the interpolate and evaluate again, right? Because that interpolate and evaluate only works for a straight line, a degree 1 polynomial. But you can as well like you can
They already have univariate polynomial.
yes.
interpolate.
Yes. So you can just use that. Your univariate polynomial would come in handy. So do you understand up to this point?
Yes.
Was it this point or this point?
If our univariate polynomial come in handy, our univariate polynomial is not giving us output in evaluation form.
The univariate polynomial.
Yes, sir.
You
It will give us, so if we use our univariate polynomial, it's going to give us the polynomial representation, but it won't be in evaluation form.
no, it won't be in evaluation form. Like you can decide to interpolate, right, and send the univariate polynomial to the verifier, or you can decide to like send 3 points. You get. But if you send 3 points, you cannot call. It will still be those 3 points will be in the evaluation, like your multilinear representation, right? And the verifier cannot evaluate. Like calling evaluate on that would be wrong. How do I explain this? Like we have the multilinear representation, right, as an array of field elements, right? Normally if you call evaluate on this, if there are 2 values, it will collapse it down to 1. If there are 4 values, like if you're partially evaluating, if there are 4 values, it will collapse it down to 2. right? But if there are 3 values and you call, say, partial evaluate or evaluate,
Cannot collapse it out.
you cannot collapse it. Even if you had a way to collapse it, anything you get will be wrong unless you convert it to a univariate polynomial by doing univariate interpolation. But we are going to, when we look at evaluation form, then would, yes, it will make sense. Okay, so the verifier sampled a random challenge, right, and sent to the prover. The prover evaluated the initial polynomial 6 a square b square at the random challenge to get 54 b square, right? And then the prover sent 54 b square to the verifier as the univariate polynomial for that round, right? The verifier evaluates it at a equal to 0 and a equal to 1, sums it up, gets 54, which is equal to the claimed sum he was expecting, right? Then it's now time for the verifier, since it's a univariate polynomial, it's now time for the verifier to do his oracle check, right? So he evaluates 54 b square at, he samples a random challenge, r equal to 2, evaluates b square at that random challenge, so gets 216, right? And also evaluates the original polynomial at the random challenges for a and b to get 216, and then the verifier accepts, right? Does it make sense? Does anybody have any other question with respect to this before we look at the product, like Sumcheck over the product of 2 multilinear polynomials? Does anybody have any question?
Is there anything going to change?
I'm looking at you. Do you have any question? Ika. Are you following? Are you following? So we have to get up to this point, right? Okay, so we are going to, okay.
I think you're saying product of
So multilinear poly.
what was the sum?
If it was a sum, you can add them together element twice. Like if it was a sum, you can add them together element twice to get one polynomial, right?
What was the sum or not the same degree? Or not the same, maybe like a square, b square plus b square, c square. You can't add it directly like that.
I just assume that. Then we can just add
Like-
0 maybe to make up
For the extra variable. But let's not go into that yet. We are still going to talk about that because you will need that when you are implementing. But let's not talk about that yet.
Not about
No, like so like are you talking with respect to the Sumcheck protocol or like
don't do some check protocol
yeah
of the sum
like
of multivariate polynomial. Is this the same way?
you can add two. Is it multivariate now or multilinear you're talking about?
Various.
A sum of multivariate. You need to like the both of them you need to represent. They need to have the same evaluation length, right? Like maybe you evaluate it over, depending on the degree. You use an interpolating set of.
But I think I saw the one you added last time. I mean, like this one. No, this is multiplication. Up, down, up.
What is
That one. So, that one now. So because no, this is the one.
okay? This one. Yeah, this is multi.
No.
Yeah, this is
What
multilinear.
happens is that if you had something like 2a square b square.
Okay. 2a square b square plus
3b square c square.
3b square c square. So if you have something like this, you will need to make the both of them the same number of variables, right? So that will be 2a square b square c to the 0, right? Plus 3a to the 0 b square c square.
What do you please?
Because like 2 square root plus 3ab.
Plus 3ab.
Yeah.
Yes.
Close.
C0. Space for 0.
Okay.
You're still going to evaluate your. Now this is 2 here, right? So you're going to use an interpolating set of 0, 1, and 2. Evaluate the 3 of them over this interpolating set, and then do element-wise summation. You do, yes, element-wise summation. Are you talking about Sumcheck or adding? Just calm down. Just relax. Okay, so let's look at the Sumcheck over the product of two multilinear. It's 3 already.
Yes.
Okay. So that's
What we'll be doing now is that once you come late, the 2 hours that you come late, we'll move it to the back.
We'll go be execution start.
Last thing I start.
People should stop coming late. Stop coming late.
Yeah, stop coming.
okay.
Last one.
Yeah.
Does this mean that in say a big triangle, in say a big triangle where we have 0, 0, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, that be the whole gate and stuff. If this stuff that you just explained now, the same operation we're going to carry out on first triangle 0, 0, 1, and then we're going to do partial.
Ask your question well so that we can hear.
Which triangle are you talking about? Is it we're performing the Sumcheck protocol on layer, not a gate? Okay, right. We're performing the Sumcheck protocol
Right
on the
now.
layer.
Yeah, like I was trying to explain, I was trying to understand that, like this Sumcheck. Oh, so the only reason why we performed it, why it was that quick for that first layer, was because there was only one gate there.
Yeah, because
So
there
that
was
means
just one
the next
gate
gate,
there.
we are going to perform Sumcheck for the first gate, then for the second gate.
No, we are not performing Sumcheck on the different gates. We are performing Sumcheck on the layer. This f of ABC polynomial is a polynomial that represents the entire layer, not a particular gate.
Yeah.
This f of ABC
Yes.
is a polynomial that represents the layer, not a particular gate.
Yes.
So when you're performing Sumcheck over this, you're performing Sumcheck over the layer, not a particular gate.
Oh, so once we are done with one particular layer, then we go to
We
the
do
next
that
layer.
reduction, then go to the next layer.
Next layer.
Yes, not gate.
Then we go, so we take that 0, 0, 0, 1, 10, 0, 0. So we take that output that we got from the first gate as for the second gate. Yeah, like as that's the.
We'll get 2 new
Yes.
Sumchecks.
Yes.
Yeah. Then we continue like that. Use that and prove it like the relationship between that one and the layer beneath. And we just keep going down until we get to the input.
So we're not going to do that, summing the two values together to concat it. He was saying something like, by the time you
by the time you explode it, if you don't bring it together, it will continue increasing. Like
No, like you can.
Well, I know we can't enter that one. That is the one you said after.
Yes.
So for now, do we just do the one of like? Do we just do the
For
one
now,
of-
we should just understand
So the one that
what.
expands and
Yes. For now, we should just understand what we are. I think it's already 3:23. So I think tomorrow. Huh? Yeah, it's 3:23 already. Oh. Shit.
I'm sure
That means basically like we thought we had gotten like, so I say leverage based on time, but it seems we are back at 50%. No, like this week is over already now. Like
Anything we make a carry can come down.
this week is over already. Man, there's a lot. There's a lot to do. You guys should just be prepared.
Never hear his voice.